Emily du Châtelet showed that vis viva, or kinetic energy, is conserved. But we can generalize this idea to all forms of energy, not just kinetic energy. Energy is conserved in all closed systems, but only if all forms of energy that are present are taken into account. And there are many, many forms. There's kinetic and gravitational energy, yes, but then there's also elastic and electric potential energy, translational energy, rotational energy, vibrational energy, light energy, sound energy, thermal energy, vacuum energy, chemical energy, nuclear energy. The list goes on. They all have their respective formulae, but can be categorized as either kinetic energy or potential energy. These are the two major types. If we press the brakes to stop a moving car, our velocity decreases and so does the kinetic energy. The kinetic energy was not destroyed, it was just converted into heat energy as the brakes that we pressed on slowed the car and heated the moving wheels through the force of friction. If we apply the work energy theorem here, we see that the change in kinetic energy of the car was minus 312,500 joules. Since the value for work done on the car is negative, we don't say that the car had work done upon it. Rather, the car did work upon something else and gave its kinetic energy up as heat to the surroundings and sound as well. When I dropped the ball transferred energy to the ground and the surrounding air in the form of heat from friction, and some energy was expended in the sound of the ball-ground collision. When I lifted the ball in the first place, I converted a bit of the chemical energy in my body into the gravitational energy of the ball. I did work on the ball as I moved it upward by some distance. The ball's energy increased henceforth, and it gained the ability to do stuff. Fall down, that is. As it fell down, the gravitational energy of the ball slowly converted into kinetic energy, and at the instant before impact, all of the gravitational energy of the ball converted into kinetic energy. At the beginning, the ball had only gravitational potential energy and zero kinetic energy. In the end, the ball had only kinetic energy and zero gravitational energy, and the total energy was the same. This principle of conservation also works when the ball is flying as a projectile in 2 dimensions or in 3 dimensions. The bottom line: energy is conserved. Kinetic energy is the energy of motion, and potential energy is the energy of position in a field. But position and motion are relative, they depend on your reference frame. There is no such thing as absolute motion or position. And so that also means there is no such thing as absolute energy. Energy depends on your frame of reference. It does. I push on a large table along the surface of the earth so that it's traveling at a ridiculous 5 meters per second. Yes, I'm quite strong. And on the table itself, a marble is rolling at a velocity of 0.5 meters per second. If Jonathan Shetty were to stand on the surface of the table and measure the velocity of the ball with a velocity gun, he'd see that it would be traveling at a velocity of 0.5 meters per second. If Sunita Ghiwala were to do the same, but while standing on the ground, he would measure the ball's velocity to be around about 5.5 meters per second. And if Ray Robinson were to do this from the surface of the sun, he can, he would see that the marble would have a velocity of 35.5 meters per second. This is the sum of the velocity of the orbiting Earth, the velocity of the marble on the table, and the velocity of the table on the Earth. Each of these 3 people measured a different value for velocity and the subsequent kinetic energy of the ball. So, which of these people had the right value? Well, there is no right value. All reference frames are equally valid. All of their velocity measurements and energy calculations were correct. The kinetic energy depends on your point of view. We say it changes depending on your frame of reference. The case is similar for gravitational potential energy. To calculate, we usually consider the reference frame or 0 meter mark to be the ground. But that's not a compulsion. We can switch things up and choose our own reference point. Yes, we'll get a different value for the energy, but that doesn't really matter. Energy is just an abstract property. It's just a number. It's not tangible and extremely fundamental. It can vary, and that is totally fine. We do not care about what energy is and how much of it a system has. We are merely concerned about the change in energy of a system with time. That tells us the work done by or on an object, and therefore the stuff that happens. The law of conservation of energy may be a most useful concept in physics, but it is not a complete mechanism of nature. It is merely a claim. We can calculate some number that we call energy, and when observing the changes of nature, we come across the same number. What energy really is isn't what's most important. What's most important is that energy is always conserved. Energy and its conservation is an abstract idea which allows us to describe and make predictions about complex systems, like a collision between these two balls. The collision between the football and the marble is an example of an inelastic collision. There are two main types of collisions: elastic and inelastic. Elastic collisions are collisions where the kinetic energy of our system remains constant, whereas inelastic collisions are collisions where the kinetic energy of our system does not remain constant. The system here is just the two colliding bodies, the football and the marble. If this collision were elastic, then the sum of kinetic energies of these two balls would remain constant. But this collision was not elastic. That's the problem. When these two balls collided, a sound was produced. Some of the kinetic energy of those two balls went into producing that sound. Similarly, some energy was expended as heat due to the friction that was induced when these two balls came into contact. But heat and sound are difficult to avoid, at least here on Earth. Does that mean that all collisions are inelastic? Will kinetic energy always be dissipated as other forms? Pretty much, yeah. Here's another instance. We're riding a car at 25 meters per second and we crash right into a wall. Before the crash, the car had some kinetic energy, but the wall did not. After the crash, the car lost all its kinetic energy and the wall never moved to gain any of it. The kinetic energy was not destroyed. It was all just converted into heat energy and sound energy. If we calculate the very large magnitude of the heat and sound energy produced after the collision and add them up, we will see that it is equal to the kinetic energy of the car before the collision. This collision was inelastic, as the kinetic energy of the system before and after the collision was different. But if we account for all forms of energy in conversion, we see that energy as a whole is conserved in this system. Regardless of whether a collision is elastic or inelastic, just like overall energy, momentum will always be conserved too. But in general, why is momentum and energy conserved? This is a conundrum that surveys the profound systems of nature, and it's not easy to answer. Physicists were indeed struggling with energy in the 1800s. An incredible insight as to why the law of conservation of energy is a thing would come from German mathematician Emmy Noether. In 1915, Emmy Noether published her eponymous theorem, Noether's theorem. The mathematics she applied is quite complex and lies beyond the scope of this video, but let's get a conceptual sense of this theorem. So, what's Noether's theorem? Well, it's a theorem that proves that every continuous symmetry in the universe corresponds to a conserved quantity. We know by now that words used in everyday language have completely different meanings in physics. There's energy, work, and now symmetry. We can observe symmetry all around us in our daily lives. This window is symmetric because it looks the same under a mirror reflection, and so does this mouse. Similarly, this fan is symmetric under a 180-degree rotation. This kind of symmetry is not what we mean in Noether's theorem. This is a discrete symmetry. It corresponds to some kind of reflection or rotation. In Noether's theorem, we are not concerned about these. We care about continuous symmetries. Continuous symmetries are symmetries related to continuous transformations. Let's re-invoke Leibniz's pool table. This table has a perfectly flat surface upon which the balls roll. In more technical terms, we say that this table has a continuous symmetry to spatial translations. Similarly, each of the balls rolling on the table are symmetric under rotational translations. The balls and table are called coordinates, and since they're symmetric, they're called symmetric coordinates. Regardless of how much you shift and play around with each of these coordinates, Noether's theorem tells us that because the objects possess their respective symmetries, the equations of the laws of motion for the system will be eternal, will be constant. When a ball moves along this perfectly flat table that is continuously symmetric to spatial translations, the downward force of gravity is constant throughout. And Noether's theorem proves that because of this, there is a corresponding conserved quantity, momentum. When two or more balls collide along this table, their momentum is conserved because the table has a continuous symmetry to spatial translations. However, if we throw in random perturbations onto the table, a couple of bumps here and there, the spatial translation would be broken. Hence, momentum would no longer be conserved because of the ever so slightly unbalanced gravitational field of the Earth on the table. On each point, the gravitational field would vary, and so momentum would no longer be conserved. It could be lost or gained. Although the gravitational field depends on where the ball is on the table, it does not depend on when it is where it is. If a ball is placed right at the center of the table, the force of gravity on the ball due to the Earth's gravitational field, x newtons, will remain constant forever. It will be equal to x newtons today, tomorrow, next year, or even in a billion years, for the most part. If another ball collides with this ball, the results of the collision will be the same today, tomorrow, next year, and even in a billion years. The gravitational field does depend on whether the table is smooth or perturbed, but it does not depend on the time at which we are examining the table. This system is symmetric to time translations. It's time translation invariant. It doesn't care about time. If I smoothen the table and take my stopwatch, set time t equals 0 right now, and conduct the collision, the results observed will be the same as if I conduct the experiment 5 months after the timer has started. The times elapsed on the stopwatches are different, but the balls collide in the same way regardless. Time does not affect the result because the parameters do not change, namely the gravitational field, initial positions of the balls, and the force with which the moving ball is pushed. We can start our experiment at any instant in time. The system just does not care about the time of the experiment because, well, it just doesn't. And it's this time translation invariance that corresponds to the conserved quantity of energy. That's it. Energy, vis viva, energy. It's the conserved quantity in a system that's time translation invariant. This ingenious idea that relates symmetries with conservation laws, space with momentum, time with energy, is just one of Emmy Noether's many monstrous contributions to the fields of physics and mathematics. Her genius was unquestionable, but at the time and even today, to some extent, it remains underappreciated. Emmy Noether had to endure great hardship throughout her life. She was never officially recognized with the title of professor and had to fight to acquire higher level education. She lived at a time where opportunities for women were limited. She received much support from her colleagues, Felix Klein and David Hilbert. Her genius was even commended by Einstein. Eventually, she had to flee her homeland, Germany, which came under Nazi occupation. She lived for some time after in the United States, lecturing at different universities. So, no. In physics at least, energy is not this weird substance that you can sip from a can. I mean, it is weird, but it's not sippable weird. Energy is just a numerical property that objects can have. They can gain and lose it, and it comes in different forms. Energy is always conserved in our entire universe because the universe is time translation invariant. Or is it? Yes. Fine. You know what? I don't have the energy to deal with you. This is a scam. Go away. We will understand the gravity of this enigma very soon. Oh, I know what you're talking about. I lose my energy conservation every morning after I wake up. Hi. Thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.